So we mentioned that Dalton's atomic theory had some little problems with it. One of those was that he said that all atoms of a given element have the same mass. And that's sometimes called an atomic weight or an atomic mass, the mass of an atom. But it turns out that different isotopes of that element are going to have different masses. And we talked about isotopes on Tuesday. When we are dealing with elements, we are generally dealing with, honestly, mind-bogglingly large number of atoms. And so most of the time, we're just looking at, well, what is the average mass of these atoms? And so we calculate an average mass, and we call that the atomic mass, for each element. On the periodic table, that's the number directly below the element symbol. And this is the average mass of all the isotopes that compose that element. With this many atoms, you can't add them up and divide by 3, right? Because you literally don't have time in your lifetime to count even a small amount, nor could you count them. So these are calculated according to the natural abundance of each isotope. Remember we talked about neon and how it was like 90% neon 10, I think, and then there was also neon 11 and neon 12, or 20, whatever. That part, you can go back and listen to that. So, naturally occurring chlorine, there were 2 different isotopes, chlorine-35 and chlorine-37. And their relative amounts have been studied, and we know that it's 75.77% chlorine-35, 24.23% chlorine-37. The mass of chlorine-35 is 34.97 atomic mass units. That's the mass of one atom. Notice that this mass is really close to the mass number. They're almost always just a smidge smaller. And chlorine-37's mass is very close to 37, 36.97. So we're going to use the percent abundances, and this is basically calculating a weighted average. So we're going to take the percent and divide it by 100 to make it into a fraction. So the fractional amount times the mass of that element, and then we get an amount. And then we take the other isotope, its abundance expressed as a fraction, a decimal, and multiply it by its mass. This gives us another number. We add those 2 together, and we get the average atomic mass, which we just refer to as the atomic mass. So the atomic mass of chlorine is 35.45 atomic mass units. There are actually no chlorine atoms that weigh that. There's some that are heavier and some that are lighter, but this is the average, and that's what's important. So let's do an example. Magnesium has 3 naturally occurring isotopes with masses of 23.99 AMU, 24.99 AMU, and 25.98 AMU. And natural abundances of 78.99%, 10.00%, and 11.01%, respectively. Calculate the atomic mass of magnesium. So, always a good approach on problems is to go in there and highlight numbers. I'm going to kind of color code these. That's the mass of the first one, and this is the abundance of the first one. When it says respectively, it means that these values are in the same order for each property. So the second one has a mass of 24.99, and its abundance is 10%. And then the last one is 25.98, and that has 11.01% abundance. So to calculate the atomic mass, we're going to take the percent abundance, divide by 100 to make it into a fractional abundance. So 78.99% becomes 0.7899. This is like calculating the percent and stopping before you multiply by 100. So 0.7899 times the mass of that one. And then we'll go on and do the next one. So 10% becomes 0.1000 times that mass and the last guy, 0.1101%, or the fraction, and 25.98 atomic mass units. So then we can just do this whole calculation on our calculators and not write anything down until the end. 0.7899 times 23.99 plus 0.1 times 24.99 plus 0.1101 times 25.98 equals. And that's the number that my calculator gives me. Here we have adding and multiplying. So going through and following significant figure rules would be tedious, right? I'm not going to be a stickler about sig figs when you're calculating atomic masses. For one thing, after this chapter, I don't think we're going to do it again, except maybe on the final. But just here's kind of a guideline. So all of my abundances here have 4 sig figs. So I could look at my answer and say, well, 4 sig figs, that would be reasonable. And then look at our masses, not their sig figs, but their decimal places. All of these have 2 decimal places. So then it would also be reasonable to say, well, the answer should have 2 decimal places. And that ends up being the same place. So we're going to call this 24.31 atomic mass units. And we can check ourselves by looking at magnesium on the periodic table. Right? And this one says 24.3051, which if you rounded it to 2 decimal places would be 24.31. Any questions? How do we measure the mass and the abundance of atoms, isotopes? They're way, way too small to see. An important technique is called mass spectrometry. I'm not going to test you on this, but I think it's good to just be exposed to how do some of these instruments work, right? What's going on inside, just at a very basic level. So a mass spectrometer, this is a diagram. You take your sample, so maybe the magnesium, and you're going to inject it into the instrument, and so we can find out the relative abundance and the masses of the different isotopes. The first thing that happens is there's a heater that vaporizes the sample, and there's an electron beam that ionizes the sample. Even metals can be made into gases. It just has to be really hot, but it can happen. So the result is now we have charged isotopes, charged particles. The reason we want charged particles is because then we can use electric fields to make them move, and we can control them. So use electrically charged plates to accelerate these particles, and then we're going to send them through a magnetic field. They're charged, they're going through a magnetic field that's going to cause them to bend. The lightest particles will bend the most, the heaviest particles will bend the least. And then we have a detector here. And so we can measure the intensity of the signal and the position of it, and from that calculate the percent abundance and the mass of the different isotopes. Any questions? Yeah.
How did they, so you said metals, how do they vaporize metals without the machine, like,
Also melting?
Yeah.
Well, oftentimes actually they'll inject a sample of that element in solution.
Oh, okay.
So it's probably going to be magnesium ions
Okay.
that they stick in there.
Okay.
Yeah.
There's-
Yeah, because how do you stuff little chunks of magnesium in there? That would be tough. But
it's-
some people are bothered, like, well, you can't, iron's not a gas. No, you can get it in the gas phase.
Just
Not a-
dissolve it first, you're saying, and then they
Yeah.
vaporize it.
Mhm. Yep. And a mass spectrometer can be used for other things as well. We can use it to find the masses of, some unknown substance, right? And you shoot that in there and find out what the mass is. And so that can help you identify what that stuff is. It's got a lot of uses. Just going to talk about this very, very briefly. The result that you might get from the instrument is something like this, where the isotope that has the highest abundance is going to be marked as 100%, and the others are going to be relative to that. This is not the percent abundance of the element. To find the relative abundance, we have to normalize this by doing math like this to get the actual numbers. There might be a homework question like that, but that's all we're going to do with that.